Okay, hello everyone. Welcome to today's data learning talk. Today we're very happy to have Dr. Robert Peharz from Graz University of Technology. Today he will talk about probabilistic circuits and deep probabilistic models with tractable inference. Robert, I will leave the audience with you.
Okay, thanks for the invite. And I'm Robert Peharz from Graz, and so today I'll talk about one of my favorite topics, probabilistic circuits, and like how they are deep probabilistic models with tractable inference. And I've quite many. But let me start here. It's like most, if not all of you, probably have like seen these kind of models, right? So like the zoo of deep probabilistic models, right? So you probably heard about GANs, generative adversarial networks, variational autoencoders, normalizing flows, diffusion-based models, and these kind of models. So like they are all deep generative models or deep probabilistic models. And they have all one thing in common, that they essentially like want to represent a joint distribution over data. And they have like very different approaches. So for example, GANs essentially say, well, I start with some simple noise source. I filtered it through a deep neural network. And that's essentially that generates a sample. And I want to make these samples similar to real samples. And the way to do this is like having another neural network, a discriminator, which tries to distinguish fake from real samples. And the statistical underpinning for that is essentially that you are fitting essentially like a distance or divergence measure between the true data generating distribution and your synthetic distribution. VAEs are pretty similar. So like also here you have like essentially some noise source going through a neural network, which produces then a parameter over your over your observable variable. And essentially like in a nutshell, the generative model of a variational autoencode is essentially like just a big infinite mixture model where you essentially integrate out or like marginalize out the latent code, and you get essentially like a marginal density, and this is a super expressive model. Similarly, normalizing flows, again, you start with a simple noise source and essentially warp that via a chain of invertible neural networks into your data density. The advantage here, essentially, like due to invertibility, you can keep track of the density, and you can essentially perform exact maximum likelihood. You've most probably heard about diffusion-based models, so like for like models like DALI and whatnot, essentially like producing this high fidelity images. They work via essentially like essentially going from data and towards a diffusion-based diffusion process, essentially like noising up your data, trying to essentially invert this diffusion-based model so that you can actually start from some simple source and essentially generate data. So this has happened, like these and many other things have happened in the last 10 years or so. Keyword generative model, probabilistic model. But if you ask yourself, so like why is probability so important, or why do we want to have probability? And just to give a little bit about background about me, I'm a probabilistic machine learning person. So if you ask me what I'm researching, essentially I tell you I research on probabilistic machine learning. And you have to ask yourself, well, what is so special about probability? Well, first, I mean, all these generative models, of course, they are about generating new data. Yes, you want to essentially produce like similar images or similar data as your training data. And this is hard to think how to do that if you don't have probability or randomness. However, there's also like a significantly bigger story behind probability, as like my story. Essentially, probability is a consistent and optimal tool for reasoning under uncertainty. Let me give you some toy examples. So like say you want to build a cat versus dog classifier. Yeah, so here you have just two features. Yeah, so like this should illustrate a high dimensional input space, for example, images. Yeah, and say this would be the distribution, or like this would be the distribution of dogs. This would be the distribution of cats. And generally, the assumption in statistics and machine learning is that your example, so like X might be an input image, yeah, this one, for example, and Y might be the label. The general assumption is that you have like your data drawn from underlying true data generating distribution, P star. I like to call it P star because like stars are far away and out there and out of reach. And so it's usually this thing, yeah. So like we assume that our data comes from this true data generating distribution, but we don't know it. However, if you knew it, essentially what you could do is like just build up the base optimal classifier, which is just like plug in your observed image, take the conditional distribution over y, the label, and take the maximum here. So like take the most likely label given that you observe a particular image, which is, because the conditional and the joint are just proportional to each other, the same as plugging the image into your joint distribution and then maximize over the label. And this is called the base optimal classifier, and no other classifier has higher accuracy. So no deep neural network, no machine learning. Essentially, if you happen to know the true data generated distribution, you have the optimal classifier. Similarly, if you want to do regression, so like say you want to predict y, real value y from real value x, again, same story. We assume that there's some underlying distribution P star, which generates like samples, x and y samples from some distribution. Say, for example, this would be the true distribution. If we happen to know it, essentially what we can do is now compute the conditional of y given x, which is actually just the joint distribution divided by the marginal, which essentially figuratively means you slice through this joint distribution and renormalize the slices. So like for different values of x, you get like different slices. So like these, by renormalizing these are distributions over y, conditional on x. And what you could do now is essentially take the mean of all these distributions and plot essentially like a function. So this is now the mean or the expectation, the expected value of y, conditional on x. And this function has a beautiful name, namely the true regression function, which is actually no other function has lower squared loss. Yeah. So again, no machine learning, no deep neural networks. If you happen to know the actual data generating distribution, all the optimal predictors are essentially on board. Yeah. And so like so you could also like if you, for example, today you're interested in predicting y. So the joint distribution is also omnidirectional in this following sense. If today you're interested in predicting y given x and taking therefore conditional slices on x, and tomorrow you're interested in predicting x from y, and would just condition on y instead, essentially get now this other function, which is now a function of y, which is the optimal predictor for x essentially. Yeah. So essentially the way to look at the joint distribution is an omnidirectional optimal predictor. Yeah. So so there are a lot of theoretical, so like this is like actually why we are interested in probability. Probability is consistent and optimal reasoning under uncertainty. So like philosophers and their like have looked into justification of probability, Dutch book arguments, which essentially tell you if you play games, yeah, then essentially you need to obey laws of probability, or there are always situations where loss is guaranteed. If you are a fan of Yuda Pearl's work, essentially he established like analogs between probabilistic reasoning and human cognitive processes, for example, non-monotonous reasoning, explaining away. Or there's also this famous Cox theorem, which essentially establishes under reasonable soft plausibility assumptions that probability is the only reasonable extension of logic to soft real numbers, so essentially incorporating uncertainty. Or as Laplace put it, probability is nothing but common sense reduced to computation. And let me be slightly arrogant and put my own quote below Laplace. So maybe if Laplace would live today and knew what AI was, so I actually don't know what AI is, and you also don't know, so nobody knows really what AI is, but a key feature of AI is probably to have consistent reasoning under uncertainty. And essentially, that's essentially the role of probability. So probability is not only about producing images or fancy images of kitties riding on unicycles and juggling chainsaws, but essentially it's like a consistent and rigorous reasoning tool. Yeah. Okay. So like, or like put it yet in a different way. So like in my view, a joint probability distribution and GANs and VAEs and flows and so etc. They model this, right? So like a joint probability distribution in some sense is roughly a knowledge base. So it contains correlations between the variables you want to model plus uncertainty. And what do you want to do with a knowledge base? Yeah, you want to query it. And essentially this goes under the name inference routines. Yeah. So you give me a joint, and essentially I want to use this joint to answer queries I'm interested in. So of course we want sampling, that's essentially generative modeling, but we might also want to know how likely is a sample you give me under my model. So I want to evaluate density and likelihood perhaps. As said, so like in these examples about cats and dogs and these regression examples here, what I want to do is like condition or using a subroutine marginalization. So essentially marginalization means ignore stuff, for example, here Y, get it rid of your knowledge base and just get a knowledge base projected on X, for example. So X is a subset of all variables you're interested in. Conditioning is essentially just the semantics. Oh, if I happen to know X, for example, an image or a value, what is now my updated belief about the rest? Yeah, so essentially you want to inject evidence about some stuff you've observed and get like the perfect predictor. And essentially this is this. Sometimes you want to compile your distribution in some numbers, essentially expectations. Sometimes you want perhaps conditional on some other context to get the most likely configuration of your variables. That's essentially map inference, or like finding an assignment which maximizes the probability. Yeah, so essentially knowledge base plus a query language, well, that's reasoning under uncertainty, and probability has this role. Yeah. Now the key question is, can your generative model do this? Can your GAN do this? Your VAE do this? Can you do this with a flow or whatnot? The answer is actually no. So, I mean, with no, I mean, you cannot do this exactly and efficiently. So if you ask the question about all these inference routines, yeah, so, and you draw here these different models, yeah, so like these fancy deep learning models, then essentially all of them can produce samples. Some of them even can give you an exact density. But if you say you want to condition or marginalize, taking moments, maximize, taking expectations, essentially the answer is no, which means there is either no polynomial time algorithm to answer these queries exactly, or we just don't know. And typically people also don't care, because like usually they care about generating images. But as illustrated, so like probability is way bigger. It's like a consistent reasoning tool under uncertainty. So like what has happened here? So like why aren't we not taking care about this? Essentially, like this probabilistic circuit community, I'm kind of a proud fellow of, we take care about this. And essentially, probabilistic circuits are a kind of generative model where you can actually answer all these queries exactly and efficiently, often just in linear time, linear time algorithm to answer these queries exactly. Exact marginals, exact conditionings, conditionings, moments, under certain circumstances also map and expectations. Yeah. So essentially, this is my sales pitch why probabilistic circuits are interesting and important. So let me now explain what probabilistic circuits are. Yeah, definitions and inference. So you have to ask the question, if you look at this picture, PCs like really shine. And where does this come from? Essentially, from simplicity and structure. Yeah? So PCs are ultimately really simple things. If you are familiar with, say, Gaussian mixture models, essentially PCs are kind of, well, not necessarily Gaussian mixture models, but generally mixture models, and essentially like a deep version. So they're essentially like a deep generalization of vanilla mixture models. Yeah. So let me give you the basic definition. So probabilistic circuits are really simple. So you can either see them as a deep generalization of mixture models, or you can see them as a special type of neural network containing only 3 types of nodes, namely distribution nodes, which are the input on the input layer of the neural network, so to speak, so like input nodes or leaves, and like they are distribution nodes. So I will explain that a bit more. Then you have a second flavor of nodes. Some nodes are mixtures, and a third flavor, product nodes or factorization. So let me explain each of these 3 nodes in turn. So that's starting with distribution nodes. So what is a distribution node? Really simple. It's just a density, a probability mass function, or a density. Essentially like a distribution. Yeah? So like representing some distribution. So a distribution node, input node, leaf L is essentially just some, in general, simple tractable distribution function. For example, Gaussian, categorical, Poisson, gamma, exponential families, what you like. And essentially what we are doing here, we have like this network language, so to speak, and we're interpreting a distribution, a probability distribution, essentially as a nonlinear activation function in a neural network. So the semantics is, if you give me a sample that goes into my distribution node L, yeah, so in this leaf, essentially there's like a nonlinearity, and the output is really just density evaluated at X, yeah? So if this is Gaussian, like we often use these Gaussian bumps to illustrate distributions, but you're really not constrained to Gaussians. You can essentially take what you want. So if we plug in X, essentially like this value, then the output would be just P of X, so like essentially the one. Yeah, so the density evaluated at X, yeah. So really simple, interpreting a density essentially is a nonlinear activation function, so to speak. That's a distribution node. And very importantly, what PCs essentially will construct high-dimensional distributions by gluing together lower-dimensional distributions. Yeah, so we'll start with small variable scopes, so like small dimensional distributions. So these leaves are typically, if we want to model MNIST, for example, with 784 pixels, then leaves might be only maybe over a single pixel or over a bunch of 10 pixels or whatnot. So essentially just a subset. Yeah? And this is known as the scope of the leaf. Yeah. So scope of the leaf, and it's like a little bit like a receptive field in neural networks. So if you have convolution field only looks at a subfield of all inputs, and essentially like the scope is more or less the same role here. Yeah. So ideally, this distribution, in principle, the mathematics works with any kind of distribution. Ideally, you want a tractable distribution, for example, a Gaussian leaf. Yeah, so Gaussians are parameterized with a mean vector and a covariance matrix. And the good thing is, like, Gaussians are, we really like to use Gaussians in probabilistic circuits because, like, they're really nicely tractable. We know how to do sampling. That essentially works via an eigen decomposition of the covariance matrix. There's a closed form for the density. Marginalization is super easy in Gaussians. Essentially, when you want to marginalize the first variable, essentially you just need to delete the corresponding parameters. That again gives you a Gaussian, which is the marginal. There's a closed form analytic solution for conditionals. There you know the mean and the covariance of Gaussians, and you also know the max. So Gaussians are nicely tractable. And the story of probabilistic circuits essentially is like if you use tractable leaves, then the whole PC will also be tractable. Yeah? So all the inference routines which your leaves facilitate, also the whole PC will facilitate. Yeah. So this was the first node, essentially like any kind of distribution, typically simple and tractable. So the second type of node, some nodes are mixtures. So if you're familiar with Gaussian mixture models, essentially it's that. Yeah. So here, like a neural network depiction, right? So like you would have like say k different components. Yeah. So P1 up to Pk, which are really just distributions, densities all over the same scope. Yeah. So like say they would all be from pixel 1 to 100. Yeah. So like you have k different distributions, alternative distributions over the first 100 pixels in MNIST, for example. And it would essentially just take a convex combination of these. Yeah. Convex combination means a linear combination of these densities where the weights are non-negative and sum to 1. That's called a convex combination. If you're familiar with Gaussian mixture models, essentially this is a Gaussian mixture model. But here we are not confined to Gaussians, but like essentially these components are typically other nodes in the PC, like essentially input nodes in the PC. Yeah? So essentially PCs are recursive language. So we build this up top down or bottom up. Essentially we'll start with simple leaves and essentially like take mixtures of that and factorizations and so on. And essentially like, well, in neural network language, we have like these components which output the densities, these different densities. They get weighted along the way here with these weights here. And then here we just sum up, and that's the output of the sum node. Yeah. All right. So this is the second type of node, mixtures or sum nodes. And the third type is product nodes and factorization. And this can also be easily be guessed. So what it is? So say you have now k different distributions, but now, unlike as in mixture models, they are now not over the same scope, but now over disjoint sets. Yeah, for example, this might be the first 100 pixels of MNIST, second 100 pixels, blah blah blah, k 100 pixels. Yeah, so disjoint sets of variables. And a product node really computes just a factorization product of all these inputs, input densities. Yeah, so if you plug in, so if you get like here the density for the first 100 pixels, second 100 pixels, and whatnot, you really just take the product, and that's the output of this product node. Note that product nodes, so like some nodes have weights, product nodes don't have weights. Essentially, they're really just taking the product. And really, this is just like a factorization, assuming essentially some local context-specific independence. That's essentially what a product node is. And that's essentially it. And essentially now what you do is like you build up networks out of, well, these input distributions, the input layer, product nodes, and some nodes, yeah, and more product nodes, yeah. And really, so if you're familiar with Gaussian mixture models, for example, essentially like this if these two guys were Gaussian, this would be a two-component Gaussian mixture model. And the main difference is essentially in PCs is that your plate is deep. Yeah, so you're not confined to use Gaussians here. You can essentially take any distribution you like, and then you essentially just take like factorizations, mixing, factorization, mixing, deep and structured. Yeah. So this is essentially like the language of PCs. If you read PC papers, yeah, so we have this input distribution, sums and products. If you read PC papers, then you will see two technical notions, namely smoothness and decomposability, and also other notions I won't be talking about today. So smoothness really just means the following. For each sum node, it must hold that the input nodes are all over the same scope. Yeah. For example, here, these two input distributions are over orange, well, U, orange. These are over V, green. And here we take like factorizations, which have a scope orange, green. Yeah? So like U and V. And you see that this sum node essentially just takes input distributions over the orange, green scope. And same here. Yeah. Also, this guy here just takes input distribution over W, so the purple scope. Yeah. Here, this is like orange, green, purple scope. Yeah. So essentially, like this sum node also takes just distributions over the same scope. This means smoothness. Like if all your sum nodes are smooth, then your circuit is smooth. And really, what this means is that sum nodes are really just proper mixtures. Yeah, proper probabilistic mixtures. And there's this complementary notion called decomposability, which really just means that product nodes are proper factorizations. So take this product here. Yeah, so it has one orange input and one green input. Non-overlapping, same here. Non-overlapping variable scope, same here. Same here. Nope, same here. Yeah, non-overlapping variable scope, also here. Here you get like one scope orange green. It's like one node from orange green scope. Here you get one from purple scope. Decomposable, yeah. If all product nodes are decomposable, so like meaning all product nodes are just proper factorizations, then the whole circuit is decomposable. So this is like a little bit, well, smoothness, decomposability is like, well, just fancy for saying all sum nodes are proper mixtures, all product nodes are proper factorizations. So on the one hand, we want these properties because like we want to go crazy and build like really huge PCs. This is still a baby PC. So you can make them really huge and small, and they are just technical conditions to check whether everything is well defined. That's the one purpose of these two notions. The other purpose is like, if you give me a PC which is smooth and decomposable, then I can always perform marginalization and conditioning. And again, we care, if we do probability, we care about inference. We want to do marginals and conditionings because like essentially they are really core routines of probabilistic, optimal, consistent, rigorous probabilistic reasoning. So how does that work? So if we look at this PC, so how does marginalization work? It's actually really a cheap mathematical trick. So like essentially like we have this PC has like an input vector x, right? So like it's over x, that's the domain. And here at the beginning, it's split up in u, v, and w. So like they are non-overlapping subvectors of x, and together they make up x, okay? The whole thing is a density over x, okay? Now, so essentially, and evaluating the density is really just like give me values for x, yes? Like I just enter values in here and I put them in here, right? And just evaluate everything bottom up, and I just get like p of x as output. This is my model distribution, yeah? So evaluating density is closed form and exact. So how does marginalization, for example, work? For example, think that you want to marginalize a certain random variable m, yeah? So essentially what you want to do is like, well, m is just like one variable in this long vector of x, and you want to integrate it out, okay? So like essentially what p of x is essentially represented by this node, yeah? So like you apply this integral to this node, yeah? And I show you, allow me now to write this simply as this integral. And now note, well, I have an integral, I have a sum, well, I can swap, right? So I can essentially like just pull the integral down here. Yeah, so I can swap the integral with the sum node. And now recall decomposability, yeah, which means that product nodes have disjoint variable scope, which means that m only appears either here or here. So in this case, essentially, it turns out that m only appears here because m is part of u and it's not part of here, because which means this is constant with respect to m, essentially. Yeah. which means I can pull all the integrals to this left child here. Yeah, so I can distribute integrals over products because the products are decomposable. Again, here we have a sum, we can swap. Again, we have a decomposable product, we can distribute, which means the whole integral over the whole density essentially reduces to performing the corresponding integral just here at the input, and the rest of the circuit just stays the same. What this means is like if you want to integrate out m from the whole density, you just need to look where m appears at the inputs, integrate it out here. Can we do that? Sure. If this is, for example, Gaussian, just delete the parameters. So marginalization in Gaussians is trivial. So really, marginalization is really just a cheap trick, redistributing integrals to simpler factors. Yeah. Essentially, you need to replace, if this was a Gaussian over u, now you replace it over Gaussian over u without m, so marginalizing out m, which is really trivial in Gaussians, just eliminates the parameters corresponding to m. Bam, plug this in here. Now we have the marginal distribution. That's what essentially like the nice feature of PCs is like, well, they are circuits which you, or like neural networks which you can integrate, yeah, perform inference in, yeah. So marginalization, but there are also like many other tricks you can play with PCs, and I don't have time to. Like you can perform conditioning because it's essentially just using marginalization as a subroutine. You can maximize under certain additional constraints. A very nice feature is that you can essentially multiplicatively combine circuits. Essentially, you can take two circuits and combine them and take a product of these circuits, which is still a tractable circuit. And you can do like very nice advanced inference routines with that. That requires yet another property I'm not talking here about. So like, let me defer you to some nice tutorials I held together with Antonio Vergari, Yo-Chang Choi, and Guy van der Broek. So in particular, the last NeurIPS, tutorial last NeurIPS, and the ECML tutorial 20 are really nice introductions to PCs. Okay, so this is roughly what PCs are and why we care about them. They can perform exact inference. Yeah. Learning. So I won't really dive into the learning part too much. So essentially, this will be rather a crash course. But let me just tell you like the big picture, right? So PCs are, well, special kind of neural networks. So they have structure, and of course they have parameters. So therefore they are like in probabilistic graphical models and in neural networks, there are these two aspects. What is a good structure of your circuit? What are good parameters? Yeah. And essentially, if you're in machine learning, you shouldn't be surprised. Well, parameter learning essentially really follows very much like the rest of machine learning. Yeah. So what you can do if you give me a fixed structure, then I can essentially always do ADAM, SGD and ADAM, gradient-based optimization. I can optimize either the log likelihood if I want to do maximum likelihood learning, or I can also come up with discriminative objectives if I care about classification. Yeah, you can also do expectation maximization. So because PCs can be always interpreted as a latent variable model. And essentially check out my TPAMI 2007 paper and my thesis, like this, like some contribution I made and I'm pretty proud of. Under certain circumstances, there are even closed form solutions for PCs for closed form maximum likelihood if the PC is deterministic. I haven't really told you what this means, but essentially it's like another property you can impose on the PC. And you get like more inference routines and like also benefits for learning out of that. Also, people have done Bayesian parameter learning, essentially approximate Bayesian parameter learning. So if you're used to parameter learning in the rest of machine learning, there are hardly surprises. Essentially, like pretty much the same optimization routines also apply here. All right. So the more interesting part would be structure, and let me just give you the high-level idea. I mean, if you ask me what is a good structure of a PC, I want to ask you back, what is a good structure of neural networks? And how do people come up with good structures in neural networks? So like essentially it's often, well, fiddling around until something works, right? So Yann LeCun essentially was a major contribution to come up with a convolutional structure, right? And essentially this doesn't come out of thin air. It's like often trial and error, right? So sometimes you might therefore like define structures by hand. Sometimes you might want to learn them. And essentially the same applies to PCs. So like there is no one true way to come up with a good PC structure. Let me just give you the high level idea how you pick a good structure for PCs. So very often the PC structure is like just laid out via so-called region graph. And essentially like a region graph is really just like the same as a PC, but on a higher level. Really what it is, so like here's an example of a region graph. Say we have 9 random variables, so like maybe an image of 9 pixels, yeah, and we want to have a distribution over these 9 pixels. Then a region graph would contain so-called regions, these white boxes here, which have a so-called variable scope, here indicated here with this colored dots, right? So like this is the full scope. This is like a scope just containing 3 variables, another 3 variables, another 3 variables. Here this region has just 1 variable, and so on and so forth. And so, and the gray boxes are essentially like decomposition. So which means this region here over full scope is decomposed into a region containing only this scope and another region containing this scope. Note that this is like decomposable, right? So like we decompose this scope into this part and a non-overlapping other part, remaining part, yeah? And also like this goes recursive, right? So like this region graph essentially is like just a recursive decomposition of regions. So like here, this region over these 6 variables is now decomposed into, well, this region containing these 3 variables and these 3 variables, yeah? Of course, regions can also be shared, yeah? So like here, that is another decomposition, decomposing in this variable and this variable here, right? And really what this, so this region graph is just like the PC structure on a higher level. If you give me a region graph, I can just yank in here some distributions only over these 3 pixels, distributions only over these 3 pixels, distributions only over these 3 pixels, and so on and so forth. Essentially, decompositions would have like products, taking all kind of combinations of the input nodes, yeah? So this partition nodes are essentially like corresponding with products, and this inner regions are essentially corresponding to sum nodes, aka mixtures, yeah? And here you would perhaps like just have single sum nodes, so a big fat mixture over your domain. Okay, so region graphs are really just like the overall decompositional structure of the PCs. If you give me a region graph, I can convert it to a PC essentially by just throwing nodes in there. So how do I get like a good region graph? For example, you can, if you have an image domain, you could essentially like just like recursively slice up this image into 2 non-overlapping parts. Essentially, this would give you like some region graph like this. This is the so-called, yeah, so it's sometimes called the Pullman and Domingo structure, which has a pretty good inductive bias for images, for example. Or you might also use, say, something like top-down clustering. So like, for example, just clustering like k-means, which would essentially correspond to splitting up the rows of the data matrix, which essentially would, so like if you would cluster maybe the whole data matrix, you would get like 3 clusters. Each of these would then correspond to a partition, and partition node in each partition you would like then find for independent subsets. This would essentially like slice the data matrix in the other direction. You can do this like top down. This is essentially like a data-driven way to find a good structure for PCs. Sometimes also even just like no structure learning at all, just taking a random structure works well. There are also approaches to greedy structure optimization, trying to optimizing some good score, finding a good circuit which optimizes the score. Also, there's the possibility, if you give me other models like graphical models like Bayesian networks or even decision trees, I can take their structure and convert that into essentially like a corresponding probabilistic circuit structure. Again, so like this was more or less crash course, just giving you the high level picture. Yeah, so if you're lazy, just take a fixed structure and do like standard machine learning parameter learning, for example, Adam, yeah, optimizing a objective you want. If you want to have a good structure, there are ways to do that. And again, let me point you to like some recent tutorials we gave. Yeah, so this is just like giving you roughly the picture how to learn PCs. Yeah, essentially we perform machine learning just with a different architecture, long story short. So I have, I guess, roughly like 10 minutes left, and I want to show you some nice recent work we've done with PCs. So this is a paper called Einsam Networks from ICML 20. There's like a code available, and this is important because until then, probabilistic circuits were like relatively niche, and people would implement them on CPUs and like so like I personally, I did my PhD and coded it up in C++ in object-oriented manner, and it was just super slow. And then essentially TensorFlow and PyTorch and these things came along, and essentially like this was one of my projects. It was surprisingly hard, but in the end, it's no witchcraft. Essentially, the main idea is like, let us not consider individual nodes, but essentially like a vectorized representation of some nodes and product nodes. So essentially that you can essentially apply vectorization stuff. Also, be a little bit clever with bookkeeping and essentially collect many of these vectorized nodes in layers. And in the end, what you can do is like perform the whole layer in parallel with a single GPU call, with just a single call to einsam. If you don't know what einsam is, it's just the Einstein summation notation. Really, all linear algebra, all deep learning essentially can be reduced to this operation, which really just tells you, I take a tensor product and essentially sum out certain dimensions. Essentially, like the main trick here was like, well, cool, I can, what I before had to do like really individually on node basis, now I have like one big call to the GPU, computing this whole layers of probabilistic circuit layers in one go. And the result here was like roughly this. So like essentially these were previous implementations of PCs on GPU. This is like now this Einstein summations, like bigger bubble essentially means bigger model. And here we have essentially training time or run time and GPU memory. And we see, note that it's a logarithmic scale. Essentially, this was like an improvement of like 1 or 2 orders of magnitude, both in training time and GPU memory. And while these guys before were like about 50 times slower than a standard neural network, this guy is now only maybe 5 times slower than a standard neural network. And I didn't write any CUDA kernels here. I just like did some bookkeeping on PyTorch and be a little bit clever about how to organize things. And essentially with this paper, we were able to go really deep learning with PCs, yeah? So we can do now some generative modeling. So like, I mean, so like, for example, these are street view house numbers. These are real images. You can train now einsam networks essentially by expectation maximization and get now essentially like generated images here, similar for a different data set. And the real nice feature about probabilistic circuits is, well, reasoning, right? So like if I give you a test image, so this would be a test image, but actually it happens that I only have half of the test image and like the upper half is unknown. What I can do is tell, dear probabilistic circuit, here's a lower half, please condition on that and give me your conditional distribution of the upper half. Yeah, if you plug in like this lower half and you get essentially like a closed form distribution over the upper half, and then can, for example, take the expected value to do like exact imputation by doing exact inference. Yeah. So and essentially this is like really unique. You cannot do this with any other generative model. You can do exact conditioning and you can do a lot of exact reasoning tools with these things. And now essentially they also are deep learning compatible. Another thing is like what you can do is, for example, this is like a little application doing outlier detection. So say you have, say you take a probabilistic circuit like this einsam network and you train on MNIST, the training set, and then you ask like you plug in. So this is like a distribution of a pixel. So I've discarded the class value, and then I evaluate all possible all test images of MNIST, but also like test images from other data sets like Simeon. So Simeon is like looks like this, similar to MNIST, but still a little bit different. And street view house numbers is even more different. So like if I now query the model, so like how likely do you find these samples and like draw a histogram over all test samples, then you will get like something like this. So essentially the model tells you, yeah, so the test images of MNIST, they look very familiar. So I like the samples. I've seen them during training. And then you can essentially have like a cutoff here and say, well, everything in here is inlier, everything in here is outlier, yeah? So you've just trained on MNIST, but essentially you have like automatically outlier detection. So everything which looks strange and new to you is essentially like an outlier, even though you have never seen any kind of these samples before, yeah? You just realize, well, that's new, yeah? Outlier detection or novelty detection. Okay, so PCs going deep learning. Another very nice recent work is that you can also use circuits for so-called Neuro-symbolic AI. So this is a nice little paper by some of my colleagues from last year. So say you have a task where you have an an input map. Yeah, this is from Warcraft 2, and say you have like essentially 1,000 or 1,000,000 of these images, and you have like a human annotator has like drawn a shortest path, like passing grass is easy, passing forest is harder, and passing mud is also has a certain cost. Yes, like essentially this is the shortest path from the left top corner to the bottom right corner. And now if you learn a deep neural network like a ResNet, essentially like a typical test prediction will be like this. Yeah, so like your neural network essentially will predict like this, right? So like you get like an input image and will output essentially predict a binary mask, 1 where there should be path, yeah, and 0 everywhere else. And essentially the typical prediction will be something like this, because the stupid neural network has not really realized what a path really is, yeah? And now essentially the main gist here is that you can, so these probabilistic circuits are very compatible with logical circuits. So essentially what happens, long story short here essentially this is your neural network part, which outputs parameters of a so-called, of a probabilistic circuit, which essentially is a distribution over binary bit patterns, all possible binary bit patterns, yeah? And this second circuit here is essentially like a logical circuit ruling out all invalid solutions. So all bit patterns which are not a proper path from top left to bottom right. Essentially, by multiplying this, and this is like this circuit multiplication, you can rule out all impossible solutions. Now this is still a tractable circuit, so which means you can compute the partition function, which means you get actually a layer or like a distribution only over valid path given input, yeah? This is called a semantic probabilistic layer, and essentially can be more or less added as plug and play to your deep neural network, yeah? So in a nutshell, what you can do is like plugging logical constraints on the output, on the structure, on the output layer of your neural network, so that it obeys your logical rules you want to enforce, yeah? And some nice little application I did or like a master student of mine did recently. So it's for crypto side channel attacks. So essentially like the idea here is like you have some input data, you have plain text and key, you have an encryption algorithm, which is essentially like, again, a piece of logic, and you have an output like a cipher text. And encryption algorithms are like safe unless you run them on a physical device, which is actually always the case. So physical devices have like power leakages, time delays, electromagnetic emissions, heat emissions, essentially like all this physical side information, which contain information about secret, for example, your key. And so what is more or less state of the art is like, here's like a part of this crypto algorithm. Yeah, so essentially here you have your inputs that goes into your crypto algorithm. You have all these power leakages, and these power leakages essentially give you information about these intermediate results. And what you want to do is like combine these guesses together with the logic to reason back about the key. Essentially what, so SASCA, soft analytic side channel attacks, do this essentially with approximate inference via loopy belief propagation. Long story short, essentially using this kind of neuro-symbolic technique, yeah, where essentially the symbolic knowledge comes from the knowledge how the encryption algorithm works. Essentially set new state of the art by guessing, well, the key with a way higher success rate than this, like essentially SASCA with belief propagation is like success rate 90. After that, essentially you get like 98 with essentially like this exact neuro-symbolic inference algorithm based on circuits. Yeah, so this is a nice application. Also, I want to advertise a nice European project which has recently started, actually with researchers from ICL, Thomas Heinis and his team. Essentially, like the idea is like to use DNA as data storage, or essentially like using a DNA structure called DNA origamis as kind of a DNA compact disk. And again, here the large level idea is like, well, this is actually like a piece of DNA, very small scaled, and we want to print information on that, and essentially like to read the information out. We need a visual detection system, some computer vision, plus error correction codes. And essentially the idea is using circuits here to come up with a joint machine learning pipeline, essentially combining, well, this logical knowledge from error correction together with the machine learning pipeline. And this, hopefully with the result that this will be more reliable, parameter efficient, and data efficient. Yeah, so cool work together with ICL. So I guess I'm out of time and also out of slides. Yeah, so like here's a little bit more reading. So like this is a tech report from my colleagues from UCLA. This is my own thesis. As advertised, there are some nice tutorials together with Antonio Vergari, Yo-Chang Choi, and Guy van der Broek from UCLA. So I'm out of slides, out of time. Thanks for joining and thanks for listening. And I'm happy to take any questions.
Thank you, Dr. Peharz. Thank you for a nice talk. So let's see from the audience if you have any questions. So please do not hesitate to raise your hands, or you will be able to also write your questions in the chat and be able to read that. So I saw there's hands raised from Kevin. So if you want to unmute yourself.
Oh, no, thank you for the speech, but I was just clapping. It was not a hand raise.
Oh, okay. Okay. Yeah.
Thank you.
So, in fact, at the same time, I have several questions. I may start. So, I saw Dr. Peharz at the beginning of your talk and make an analogy of the PCs compared to the latent space of VAE. So, as I understand, of course, I'm not expert of PCs. So, for the version autoencoder, for example, we're dealing with continuous latent variables. And for here, with the PCs, we're dealing with discrete ones. But we know, for example, there are also some generative models which use discrete latent variables, such as vector quantized version autoencoders. I was wondering if there's any comparison or analogy that we can make between the discretized version of generative model and the one of PC.
Oops. So yeah, so you're right. So VAEs are continuous latent variable models, right? So like we have an integral here, while, and you're absolutely right, PCs are discrete latent variables. Yeah. So essentially, if you're used to this interpretation in Gaussian mixture models, right? So like also in Gaussian already in Gaussian mixture models, each sum node essentially is like a discrete latent variables with as many states as you have like inputs. Yeah, so like this would be a 3-state discrete variable. This would also be 3 states, also 3 states. Essentially, like a PC is like a hierarchical latent variable with discrete variables. Yeah, I mean there are also like intractable or generative models with discrete variables. So like this DICE model, for example, I think this was like kind of a nice paper a few years ago. So you can have also so very generally, it's like the price you have to pay is like the smoothness and decomposability, right? You need to have the structure in order to have tractability. So, well, you can have tractable and intractable discrete variable models, continuous variable models. I'd say like a main difference between continuous and discrete variables is like that all these continuous variables, what they are doing is they relate the latent code with the input, right? So which means if I have a z here, then I have a particular component over x. If I change z a little bit, I almost have the same component, right? So essentially I have like a continuous relation between my latent code and my observables. And in vanilla PCs, this is completely gone, right? So like if I have a sum node with 3 different components, they can be completely different components. And essentially, this is like a recent work we've been working on was essentially implementing little integral nodes also in PCs, right? Because like we are aware that so somehow this continuity between your observable variables and the latent variables kind of help to generalize better. And also you have like this continuous embedding, right? So like you can, like, from VAEs, you can embed this data in this latent space, yeah? You have this continuous embedding, and also this seems to somehow help generalization. So what we did recently is like try to implement little integral nodes, so like low-dimensional integral nodes also in PCs. So like this is currently a submission, and there's also another paper at AAAI, continuous mixtures of tractable models. And indeed, we see in experiments this helps, yeah. So you get, so this is the main difference, continuous embedding versus like 3 components, and these continuous embeddings do something, so like which helps generalization. And yeah, we've been working in this direction, but yeah. under submission. Does this answer your question?
Yeah, I think part of it mean that if it's continuous, so it has like a more smooth, maybe help to improve the smoothness, like, but maybe also like increase the sensitivity. I'm not sure, like in a particular application, if that would be positive or negative. Maybe it depends for the sensitivity.
Yeah, I guess so. So yeah, so somehow if you work with this real data, right, like measurements, like images and signals and so on, this kind of does a big job here, this continuous relation between X and Z. I mean, like this latent interpretation you need to do anyway with care, you need to do with care, and like so like there are some interesting groups from Copenhagen, so like Søren Hauberg, who take really care about how to make this latent space identifiable. So like this does not happen automatically, but somehow this continuous embedding does something in terms of generalization. Yeah.
Okay. Thank you, Dr. Peharz.
Yeah.
Let's see if there's a question from the audience. If not, actually, I have another question. So actually, so it's maybe more particular. So since our group, we're working on what we call multimodal data, while we do, for example, contractive learning, we do data fusion. So we're super interested in the accumulation of the latent space. So for example, here you mentioned also like the learning structure, but what you mentioned, there's a difference between like PC and like generative neural networks. So do you think that the theory that you develop with PC will help to quantify, for example, the optimality of the latent space geometry? So in the case that if we have like encoders, they issued from a contractive learning, we will be able to know when we have that by looking at the geometry in the latent space, we know when it's optimal or not. So I'm not sure if my question is clear.
I guess it, so in my opinion, structural learning is really hard, no matter where you do it, right? So, so like what you typically do in these generative modeling, so like GANs and VAEs, right? They typically take just some structure, right? And they have maybe some hyperparameters and they cross-tune that. And usually you don't really, I mean, like recent years have also seen like neural architecture search, right? So like trying to optimize structural learning. So learning structure is really hard, in my opinion, in no matter where you do it, be it in graphical models, be it in neural networks, or be it in PCs.
Yeah.
Also, I think it's very hard to talk about latent spaces and what are good latent spaces. I want again to point to the work of Søren Hauberg from Copenhagen. So like they take this question very seriously, and it's a tough question, right? So like designing latent spaces which are meaningful is like hard. Also knowing when they're meaningful is also hard. Also like constructing them is hard. So I'd say what PCs have to offer is, well, naturally they have like this discrete latent space, right? So like it's rather than having like a VAE embedding as a continuous vector, you would essentially have now a discrete vector, which is also like hierarchical. There's actually a paper by Antonio Vergari, and I'm also a co-author of that. Essentially, it's called Sum Product Autoencoding, which really just like trains a PC, a sum product network, which is essentially a different word for PC, training a PC from data, and essentially like using this latent variable interpretation as discrete latent variables to, well, we plug in data, so X, and we infer like the most likely state Z, which is now a discrete vector. I'd say this can be interesting, especially if you mix it with, like if you want to have something like latent embedding, which has both discrete variables and continuous variables. This can be interesting. So saying when do we have the right latent space, I don't say it, so it makes sense to talk about latent spaces, but I think this is a really hard question. Again, advertising Søren Hauberg's work from Copenhagen. So like taking this question seriously, what is the correct latent space, is tough and usually, well, not identifiable. To make this identifiable is a tough problem. So structure and latent spaces are hard. So conceptually hard. Sorry? Yeah?
I mean, it's still very open. As you said, it's a hard question.
Yeah. So, yeah, I would say you can't just like train some VAE and say, well, this learns the latent structure, right? It's like, no. So things go wrong. Latent structure is generally ill-posed, right? So ill-posed, often not identifiable, right? So it will learn something, right? So, but so latent structure needs to be interpreted really with care. That's my opinion. Yeah.
Okay. Thank you very much for your insightful discussion. So, if there's no question from the audience, I think we're already around 5 p.m. in the UK. So, I would like just to thank you again for Dr. Peharz for joining us, for accepting our invitation, and for the nice presentation and discussion. And thank you for all the audience who have joined us this evening. And yeah, for people in Europe, in the UK, have a nice evening, and for people in the US, have a nice day. Thank you very much.
Yeah, thanks for having me, and for joining my talk. If there are any follow-up questions, like, please, everybody feel free to shoot me an email.
Thank you, everyone. Bye. Take care.
Thank you. Bye-bye.